I wonder if we could just get back a little bit more into the basics and talk about how electric muscle stimulation, what it is and how it works and why it's essential to understand for the world you're operating in.
Absolutely. So as I said, one way to move the body is with big robotic exoskeletons, these big motors attached to your body. Turns out to be very inconvenient. They're large, they're heavy, they're cumbersome. And in some industries, we might start to see those devices pop up, but for everyday use, they're just very cumbersome. And so one way that we can get inspired by inventions in medicine is by sort of looking at other ways to move the body. And electrical muscle stimulation is one such way. This is a technology that is extremely old. It looks very sci-fi and new. It uses little electrodes, little patches that you can put on top of your muscles that look like this. And you pass a little electrical current through the inside of your body, a very, very tiny amount of current. And because your muscles are little electrical machines, once they feel the presence of the electrical energy, they will actually contract. That is how your brain controls your muscles, by sending those impulses. So we're just mimicking those impulses and letting the muscles contract. Now, what we're doing is sort of asking the same questions that roboticists have asked with the motors, but we're asking with the muscle stimulation. Roboticists said, can we help people move with these exoskeletons by sending the computer control to the motors that help the body move and maybe pick up a box that otherwise you couldn't, or balance in a situation where you would have a hard time balancing. Now we're doing this directly to your muscles rather than indirectly through this exoskeleton. So we're sending these computerized electrical impulses at the right time, at the right moment, to rebalance your body, to move your body in ways that give you a sense that you're being controlled, but also a sense that you're doing the movement. And this is where it gets really different from the exoskeletons. It's really interesting. If you're wearing this exoskeleton, you have to almost imagine Pinocchio's father puppeteering you.
Yes, yes.
And you're being moved by it. Whereas if your body is being controlled by the muscle stimulation, to some degree you're being puppeteered by this computer. And again, we'll talk about the dystopian angles in just a second. But it is your body that is moving. You actually feel your muscles contracting. You immediately know which muscle to move with how much force, because in the end of the day, it's exactly what you do when you contract your muscles.
What is happening between your brain and the muscles at this point?
Yeah, that is a wonderful question. And the reason why I started to work with some neuroscientists here at the university, I'll just briefly mention Howard Nussbaum as one of the people who's been helping me understand that puzzle, what happens when the muscles are moved externally, but my brain has to reason backwards of, wait a second, we didn't send this command to move, but now the muscles are moving, has been Howard Nussbaum in psychology. So we move your muscles through these electrical impulses, and your brain now has to wrestle with this command that was never initiated by your own body. So it creates a sense of conflict that you feel. The muscle is contracting, your brain is confused by that. Sometimes people call that a sensory conflict. Similar to how maybe you felt, Paul, if you are in the car and you start to feel nauseated because your eyes see movement, but your body is not moving. That's typically how people explain this sense of dizziness with car sickness, right? This is a type of conflict too, where your body is moving, but your brain didn't instruct it to move. So one thing that we do at an engineering level is, can we fix that conflict, right? Can we, for example, wait a little bit, and instead of moving you very rapidly and very early, almost like it would be surprising, we actually wait for your brain to generate the wish of moving, and now you have intended to move. We can still help you move, but we waited for you to move. So you no longer have this sensory conflict of, I never wanted to move and I'm moving. Now you wanted to move and you are moving. But we are able to help you move, maybe with the right force, with the right timing, and with the right balance. That's one way we can solve that conflict.
Tell me what reactions you've seen for users and how do they experience what you're talking about?
I must say that the most common reaction at the very first time you try this is laughter. And I've asked the neuroscientists and I've asked the psychologists, and they also don't know why this happens. It's very, very interesting. People look at their hands, and especially we do a lot of stimulation on the hands, helping people, for example, learn how to operate tools they've never seen before. Imagining you're a carpenter, first day of the job, and they tell you, like, please use that chisel, and you've never even heard a word chisel before, and you grab the tool and automatically the muscle stimulation starts to perform that smooth movement.
Holy cow.
And you go like,
Wow.
oh, that's what a chisel do. The first thing they do is look at their hands, very surprised, and they laugh. I think the laughter is partially almost like a way to resolve this discomfort and resolve this surprise. And as a podcaster, you know that laughter has many, many shapes, not just when things are funny, but also when things are surprising, when things are weird, we laugh. What is surprising, though, is very rapidly, and I think this is because it's haptics. It doesn't need to be explained to people. We actually do very little talking in these experiments because people very rapidly understand, oh, this is doing X, this is my body doing. We've actually put people through experiments where we asked them to manipulate tools they've never seen before, really strange tools like a magnetic sweeper. It's something in factories you use if you drop 1,000 nails on the floor and you go like, who's going to pick those up? You have a little sweeper to pick them up that has a magnet inside. But if you've never worked in a factory, you have no idea what a magnetic sweeper is. We give this thing to people, we throw 1,000 nails on the floor, they have no idea how to use a magnetic sweeper, but we stimulate their bodies to start perform the right movements, and they very rapidly, within seconds after the laughter ceases, they really rapidly understand not only what the tool does, but even what the mechanisms. The magnetic sweeper has a little latch that you have to disengage for the magnet to move. They very rapidly understand my hand is doing the right movements. I now understand how this tool works, and sometimes even infer the mechanism. And I should really emphasize that we're not exploring this as an opposition to watching videos and learning from mentors. The idea is that you could do all of them now, right? You could have also a video telling you this is a magnetic sweeper, and it works like that. But imagine having all this extremely rich information entering your body at the moment you're learning. And so the other reaction that we've had is when we do experiments that endow people with an ability to do something they've never done before. For example, we had a long project that just finished where we were helping people learn musical skills. We put their hands on a piano and we're going to move their fingers independently to play a melody they've never played before. And people love learning a melody like that, right? It's not the same as watching a video. We've actually compared it to watching a video, and this is potentially a little bit faster. It's not the same as copying a teacher. Copying a teacher is very good. We as humans have evolved by copying each other very well, so we have a big brain infrastructure for copying movements. But there are things that are difficult to copy. I don't know how much force you put in each key of the piano, the intensity of a note. But if you feel it, you immediately know it. So people have a kick out of feeling those sensations, how much force to put in each melody, in each note.
And Pedro, if I came back the next day and I'm not hooked up, could I remember what I had learned better than I would have previously?
That's exactly what the experiment was about. So you're really right on the experimental design. So we weren't just trying to understand. So we didn't do a full day, but we sent you away. So you come, you learn the melody. We train you immediately after, but we weren't looking at that training. That training is of course good. People are good at learning. But then we send you away and without you knowing that you're going to come back. And then we call you a few hours later and say, hey, you know what? We forgot something. And then you come back and we say, actually, we didn't forget anything. You have to play the melody again, unassisted. Muscle stimulation is out the window. The device isn't even there. Do you still remember? In the group that trained with muscle stimulation remembers it better. And in fact, we even found the same thing that you find in education studies, which is not only the muscle stimulation should constantly tell you what the melody is, but it should actually help you where you make mistakes. So we had actually a group that experienced also the muscle stimulation, but it only intervened when you made a mistake, right? If you're good, it just lets you play. And then the moment you make a mistake, it says, it was actually not that finger. It's not the index in this part, it's the ring finger. Only kicks in there and corrects that mistake. That group remembers it even better than the other group.